Welcome to the Che Institute's Scientific Innovation Series, New Era of Space Exploration. My name is Young-Ki Kim. I'm professor of physics at the University of Chicago. Today, we have three distinguished scholars in space science joining us, and they will cover topics such as gravitational waves, asteroid exploration, and satellite proximity navigation. Before we officially kick off the seminar, it is my great pleasure to introduce In-Guk Park, president of the Che Institute for Advanced Studies, who will deliver welcoming remarks. Let us extend a warm round of applause to welcome him to the stage.
Good afternoon, ladies and gentlemen. It is my pleasure to be here as a co-host of today's special forum, New Era of Space Exploration. If you allow me, I would like to take this opportunity to introduce our organization, Che Institute for Advanced Studies. The Che Institute was established in 2018 in commemoration of founding chairman of SK Group, Choi Jong-hyun. Our institute has three missions. First, identify geopolitical risk. Second, explore the limits of scientific innovation. Third, examine the impact of scientific innovation on geopolitical dynamics. To this effect, the Che Institute has been hosting the Trans-Pacific Dialogue, a signature international conference lasting 3 days in Washington, D.C. This annual conference has been blessed by participation of the world's most influential opinion leaders, scholars, and high-ranking officials from US, Korea, and Japan. We also examined the impact of strategic competition and global supply chain disruptions in critical technology sectors, such as semiconductors, EV batteries, and biotechnology. In addition, the Che Institute maintains and deepens partnership with leading global think tank, including CSIS and Land Corporation, etc. Recently, the Che Institute launched the Che Scientific Advisory Committee, consisting of 50 world-class scholars in Korea and the United States, including Dr. Young-Ki Kim, who is with us here today as the chair of this forum. Today, I'm very pleased to welcome Professor Barry Barish, a Nobel laureate in physics, as well as Professor Daniel Shears and Professor Hyo-Chung Bang, distinguished scholars in the fields of asteroid exploration and satellite technology, respectively. Especially, I want to thank Professor Barish for taking the trouble to present at this afternoon forum, on top of his wonderful keynote speeches during the plenary session this morning. I also want to send my special thanks to Dr. Sears, who has been recognized as top-notch pioneer in major astronaut exploration missions. Over the years, Korea has made significant strides in space research and innovation and has elevated its position on the global stage. Last year, Korea has successfully launched Danuri, the first lunar orbiter, and Nuri, the first indigenously developed space rocket. Korea continues to show its dedication to pushing boundaries and achieving new milestones. Though Korea may be a latecomer in this race to space, such remarkable achievement is a clear indication of its future potential as a major player in space technologies. As we gather here with the prominent members of the Korean American Scientists and Engineers Association, I hope that today's forum serves to trigger new momentum and generate collective wisdom for all of us traveling this uncharted path. I thank you.
I'm going to talk today about an emerging field which will be very much parallel to the heart of space science, which is astronomy. But astronomy presently done with electromagnetic waves, and we will see as we move forward that the same science problems will be explored, some in space and some on the ground, just like in astronomy and cosmology for gravitational waves. And so, in some sense, my talk is a preview of the science to come, the space science to come. I will start by talking about advances beyond what we've reported so far on the ground and covering so you can see the whole era of space. In order for us to look at objects in space, and in order for us to integrate gravitational wave science with electromagnetic wave science, which is astronomy, we need to be able to point or know where objects are that we're studying in space so that we can correlate the information that comes from the gravitational waves with information that will come from telescopes or satellites. And so that has been done at least once in a very important experiment which demonstrates the ability to do this. And so what is done is illustrated here. We triangulate from the object by looking at the same phenomenon at 3 different points on the Earth. So this is involving triangulation, which involves our ability to point. This requires an advance that we have been making in gravitational wave science, and that is to actually be able to instantly identify that we see something interesting astronomically or cosmologically in space so that we can reconstruct the position of that object and alert the astronomical community. I'll point out that gravitational wave detectors see all of space all the time so that we don't have to point. But in order to correlate with electromagnetic telescopes, we need to be able to tell them with some accuracy where something is interesting in space. And we use triangulation to do that. We presently are able to do that by the fact that LIGO, the detector I've been involved in, has 2 detectors. That doesn't allow us to get an accurate pointing. But by adding a new detector in Italy called Virgo, we're able to triangulate. So the triangulation comes from the combination of the 3, and this famous event that we saw was able to do that because of the triangulation. This was the observation of high-energy gamma rays in a satellite called Fermi, and in a second satellite as well, at the same time, or nearly the same time, as the observation in LIGO. So we basically were able to do this with a combination of information on electromagnetic waves in satellites and the information, in this case, on the ground in LIGO. The signal from gravitational waves is shown on the left, and the lower graph, which is a time versus frequency graph. As time goes to the right, you'll see that it bends up as the frequency goes to higher. That's the actual identification of the signal of, in this case, 2 neutron stars merging and forming a combined object. That was then observed by the Fermi satellite by detecting very high energy gamma rays, and they're pointing in the sky. They're pointing in the sky as shown in the right, in the very large circle. And the banana-shaped one is the pointing from LIGO. So this coincidence enabled us to alert the whole astronomical community to look at that place in the sky and follow the signal from the merger of a neutron star, which is the first time this has ever been done. It was the largest mobilization of astronomical instruments ever by alerting them early. And the signal was followed, as I'll show you, out to different frequencies. So the first thing to notice is that the gravitational wave signal comes at almost the same time as the electromagnetic signal, but actually 2 seconds before. The object, which I'll show you, is in a galaxy that's 150 million light years from the Earth. That's 1.5 10 to the 15 seconds. And since they're within 2 seconds of each other, it means that the speed of light and the speed of gravitational waves are the same to 1 part in 10 to the 15, as proposed by Einstein when he proposed that there were gravitational waves, that there's one speed and the gravity travels at the same speed. Newton, in Newton's theory of gravity, which we all learned in school, the travel happens instantaneously. And that's called instantaneous action at a distance. And it's one of the problems that Einstein solved when he introduced his theory of gravity. This is now an image of locating where it was. If we keep pointing in the sky, we found the galaxy where it started, which was the one which is shown here, 150 million light years away. And it was from that place that we then alerted the astronomical community to look at the light in different wavelengths that comes from this signal, which is shown here. This then was, this information was used for physics experiments. In this case, the fact that we have an independent way using gravity to measure the speed at which the universe is expanding, what's called the Hubble constant. And it has been a problem in astronomy that by 2 different methods, the answer doesn't quite agree, and yet this is the important measurement of what's happening in the expansion of the universe. We have an independent way in the future to measure this constant through gravitational waves. As shown with only this single observation, we're not able to resolve the discrepancy that exists, but in the coming years, we will obtain roughly 100 events by 2030, in which case, if it isn't resolved by the astronomers, it will be resolved through the addition of information from gravitational waves. Once the signal was found, in this case very early, the whole astronomical community was alerted. This varied from visible light to all the way to radio waves, high energy gamma rays, where it started, and even a search for seeing if there were neutrinos from this object, which weren't seen. This then followed the evolution of this device, of this merger of 2 neutron stars, starting from high energy gamma, starting from gravitational waves, then very quickly after that, high energy gamma rays, and all the way out for several weeks until we got to the radio waves. This combined data with 2,000 different astronomical objects and enabled for the first time, the determination of what we call the equation of state for a neutron star, or understanding what the dynamics are of a neutron star. This is just the data as you change from wavelength as it evolves in time. And the final signal for this. As we move forward, gravitational waves will be done just like astronomy, both in space and here on the ground. The next possible device is shown in where it'll be in this graph here. What I show on the horizontal axis is frequency. LIGO is at very high frequencies. It's the frequencies that are enabled, that we're able to build an instrument on the Earth's surface, and that's the audio band, 10 hertz to 10,000 hertz. The first ambitious device that'll go in space is called LISA. That stands for Laser Interferometer Space Antenna. And it'll go in space. I'll talk about it in a moment. And it covers the region from 10 to the minus 2 to 10 to the minus 5 hertz. And then a third device measures the accurate timing or differences in timing that comes from pulsars, pulsar timing array. And they recently have a result that I'll show you. The pulsar timing array is shown here. The idea is that pulsars are very accurate clocks, and they monitor the time in all of them together. And if a gravitational wave at very low frequencies goes through space, that distorts the timing a little bit in a known way that you can look for. And recently, there's at least the tempting evidence in the last month that maybe such a signal has been seen. I show that here. This is from the very recent last weeks of data brought forward by the pulsar timing arrays. What you notice is the correlation of the signal that is seen or difference from the horizontal line, which would be what you expect with nothing passing through. The distortion has a shape which goes down and up as a function of the separation of the pulsars that are timed. And it's expected to have a shape like the dashed line. The data is not good enough yet to establish at high confidence that that's what's being seen, but it's very tempting, especially with the characteristic looking right. These low frequency gravitational waves are also the equivalent of what's done in astronomy to go to low frequencies and get information on the early universe. Lastly, the interpretation of what they think they see in what I've just shown is the possible a pair of supermassive black holes. We had detected not supermassive, but solar type black holes. And this is in a computer simulation. So this is the, if you want, a probable candidate for the data that's just been shown if it holds up as they establish more data. The most ambitious project is to come in space. It originally was a combined project, 50-50 collaboration between NASA and ESA. But as the James Webb Telescope was delayed and cost more money, the American part was dropped out, and it's now a primarily European project with a small contribution by NASA. It involves 3 satellites, 2.5, 10 to the 6 kilometers apart, and basically the idea is the same, that the timing of those is set when nothing's happening, and if a gravitational wave goes through, it upsets the timing in a way that can be recorded. This sits in space at 1 astronomical unit from the sun in an orbit like I show here, and that's the orbit that it'll be in. Its mission is presently scheduled for 2034. This is where just a picture of its sensitivity, the line, with a little wiggles is the sensitivity. The frequency, as I showed you, is tenths from 10 to the minus 1 or 2 to 10 to the minus 4 hertz. And what's shown on there is just symbols of some of the possible detections that will be made at the lower frequency from known objects like white dwarf, double white dwarfs, or supermassive and intermediate mass black holes. The project itself has been developed through serious R&D worldwide, including the US and mostly in Germany and Italy. And they had a test mission which was called the Pathfinder, LISA Pathfinder, which flew in 2018. And it established that technically they can reach the requirements of the detector on the main questions that existed. The main question was to have inside the satellite the ability to have the masses be free to move so that if gravitational comes by, it can move the masses. And that records the signal, and that technology has been proven. It basically is not quite an interferometer in the same sense as LIGO is. It uses a system of basically first a free masses inside the satellite, and it sends laser beams and has recorders, responders, and transmitters in this triangular shape that I showed. The last thing that I'll show is that the last part of understanding gravitational waves actually comes from the cosmic microwave background signal in electromagnetic waves. New facilities are being developed now that are capable of measuring this more accurately than in the past. And when they're measured accurately enough, we can see the imprint of gravitational waves, we think, or hope, on the cosmic wave background signal. The cosmic microwave background signal is a photograph, basically, of what the universe looked like 400,000 years after the Big Bang. You can't go back earlier because it's opaque to electromagnetic radiation. But the belief now is that we can see something about what happened earlier by seeing the polarization modes that are an imprint of the gravitational waves from earlier in time. So the gravitational wave signal can give an imprint on the cosmic microwave background signal, and in that way we can see earlier in time and maybe understand questions, for example, now like what we call inflation in the early universe. So this is basically a global picture of what will be done. I show basically on the horizontal axis the frequency going from our time going on the very right from milliseconds up to on the very left, very, very, very low frequencies, or back to the Big Bang. As you can see, LIGO is way on the right and measures basically as far as we can be from the Big Bang. So it's the new devices that move us toward the left that will enable us to see information on the age of the universe or the early times. And with that, I thank you.
So today I'm going to talk about sort of a different range of masses than what we've just heard about. So Professor Barish was talking about maybe the most massive objects in the universe. When we talk about asteroids, they're not the smallest objects, but they are among the smallest objects in the solar system. And they really serve as an interesting counterpart at the other end of the scale, if you will. So I'm going to talk a bit about some previous asteroid missions that have occurred, some future asteroid missions, but instead of just focusing on that, I think it's more important to first talk a bit about what these objects are, since they may not be familiar to everyone, and the motivation for the study of these may not be that familiar as well. So first, I'm going to talk a bit about what asteroids are, just so we have a good common place to start from. And actually what I have here are various models and measurements and computations of different asteroidal bodies. And the one thing we can see is that they have a wide range of shapes and morphologies that can occur. Asteroids themselves are just small bodies in the solar system that orbit the sun. And this is just a snapshot showing a number of the different asteroids orbiting. And you see the planets in here, Earth, Mars, Venus. And this is, of course, the main asteroid belt. We also see intersecting the orbit of the Earth and even Venus and Mars are many other asteroids as well. And these are called near-Earth asteroids, and they play a special role in why we study these bodies. I think it's also interesting to give you a sense of size scale about these bodies. So we'll sort of walk very quickly down a variety of size scales, and starting with the Earth, of course, which we're familiar with, the Moon, and then the largest of the asteroids, Ceres. And if we jump to the next slide, here's Ceres blown up again. And the next 4 or 3 largest asteroids, which actually have been recategorized as of a decade or so ago into some of these are now dwarf planets and are no longer asteroids. That happened when Pluto got kicked out of the solar system. I was at the meeting when that happened. It was traumatic for some people. So if we then focus on Vesta and go to the next size scale, here we have Vesta, and then these are more common representations of asteroids that we've flown by in the past across the solar system. And we'll focus on this very smallest one, which we can't even see yet, the asteroid Itokawa, because this is one that we'll talk briefly about in a few slides. So if we focus on this one, Lutetia, which was flown by the Rosetta spacecraft, and now we have this in full size scale, we see a variety of other asteroids that we have flown by and comets as well. And this guy here, Itokawa, you can now see that it's just a pixel. It's so small. What I'm trying to show with this set of slides is that there's a huge size scale of bodies that we deal with when we are investigating asteroids and sending spacecraft to visit these bodies. And it's a very interesting technical challenge to design spacecraft and operations that will work across the whole range of size and mass of these bodies. So with that as a very elementary introduction to asteroids, it's a good motivation to talk a little bit about why we're interested and why we spend time and resources studying these bodies. And the main motivation for doing this is really science and to understand more fully nature. The asteroids that we study, that we fly to, are actually remnants of the very early solar system. And they actually preserve and provide, in some cases, a pristine record of the cosmochemistry that was occurring when the planets formed in the very early protoplanetary disk. Also, just study of asteroids and their classification and where they're distributed in the solar system also give us insight into how the major planets of the solar system may have migrated and moved over the last 4 billion years. Also, by studying asteroids, we can understand how they've shaped life on Earth, delivering water and minerals to the early Earth, resetting life on the Earth once in a while through large-scale impacts. And in a very interesting way, especially when we study the very smallest asteroids, they're what we call a microgravity aggregate, and they're really a unique form of matter, where the gravitational attractions are as strong as the van der Waals attractions that can exist between the particles. And when you have these things rotating, you come up with a very interesting sort of a tenuous state of matter that is geophysically relevant in the solar system. So by understanding bodies in that perspective as well, we get a lot of interesting insights into the geophysics of these very microgravity aggregates. Another motivation is exploration. Near-Earth asteroids are one of the most accessible bodies in the solar system. And they've been studied by NASA as potential future targets for astronauts. I think right now the focus is back on the moon, but it could very easily at some point in the future come back to asteroids. And of course, there's a lot of science fiction behind that, but it's also something that is feasible, although very difficult to do with humans, of course. Another very large motivation at times is resources. And there's an understanding that asteroids have very potentially valuable collections of minerals and water and the like in space that might be uniquely accessible. And there have been many stories, of course, written about this. There have been many companies started in order to start to plan and make plans for resource utilization of asteroids. This one here, Planetary Resources, they had a very compelling science case and business case, really, about how you could extract water from asteroids, from primitive asteroids, and use that to fuel a lot of activities in space. But it's also a cautionary tale, since they went bankrupt about 4 or 5 years ago. So it's a very, it's potentially a topic that's not ready for prime time yet, but there are always new companies starting. One new one that's just located in Colorado, Carbon Plus, is again has a business plan that they are confident of and are aggressively moving forward. So this is a topic for why people like to study asteroids. Maybe the most compelling reason to study asteroids is when we think about society as we go into the future. Because we know that these small bodies are always impacting the Earth. You know, the Chelyabinsk from a few years ago, shooting stars at night. These are all asteroids that are then interacting with the Earth. We also know from the geological record that occasionally we have very large asteroids that can impact, that can actually change and reset life on the planet. So there is a compelling question for why we study asteroids is, if we did at some point in the future detect one on a collision course, could we actually do something from a societal perspective to avert that disaster? And in fact, the recent NASA DART mission from last year actually was the first planetary defense mission that NASA flew, which was actually to test basic technology for pushing or nudging one of these hazardous asteroids out of the way. I'll talk a little bit more about that in a bit. So with that as sort of an overview for why we're interested in studying these bodies, we can talk a little bit about some of the missions that have occurred in the past and some of the interesting things that we've found and done in this environment. So here's sort of a collection of many of the different bodies that we've either flown by or orbited or interacted with at some level in the past. And I'll talk briefly about a few of these different targets. The first one the first time that we actually visited and stopped at an asteroid to explore it in detail was the Near-Earth Asteroid Rendezvous mission. And this goes back into the mid-90s, and actually it culminated by landing on the surface of its target asteroid, Eros, in 2001. And this was the first time we actually had a comprehensive mapping of an asteroid. And it's just very interesting to see the very irregular shape of this body, and there was a lot of fundamental science that was done. Here's another view of the asteroid, and here you can see for scale the Empire State Building. So this is maybe the size of Manhattan, and you see boulders on the surface of this that could be as large as an office building or this hotel that we're in right now. The next important mission to visit an asteroid was the Hayabusa mission, which was run by the Japanese Space Agency. This was launched in a few years after the NEAR mission landed, and it arrived at its asteroid Itokawa, and this was the pixel that I was showing you earlier. And now you can see, again, the size scale, where this asteroid is about the size of the Empire State Building, whereas if we go back to this slide, we see how small that is compared to this asteroid, Eros, just giving you, again, a sense of the scale that occurs. This was an important epoch because this was the first time we actually sampled the surface of an asteroid and brought some of these pristine materials back to Earth where they could be studied in great detail. And there's a lot of interesting stories about this mission, but I'll move on. The next important epoch is the Hayabusa 2 mission, which launched about a little over a decade after the Hayabusa mission. This again was a mission from the Japanese Space Agency, and this one was much more aggressive in terms of the sort of activities that it carried out. And it goes beyond, it is fundamentally a sample return mission, and in fact, the sample from the asteroid it visited, which was a very primitive carbonaceous asteroid, is actually in the laboratories now and is being studied. But they also had a lot of other activities that they carried out. Up here, this is just a sequence of images from the sampling attempt. And you see they went and they touched down on the surface of this asteroid that they visited, called Ryugu. And the gravity is so low that as they pushed off away from the body, they actually brought the whole host of boulders and large rocks that were just levitated by the jets and, if you will, chased the spacecraft as it departed. They also carried on board an explosive device that actually shot a pellet into the surface of the asteroid, and they actually created a crater, which was one way of testing the geomechanical properties of that asteroid, a very innovative approach. And what they did with this is they exposed material that was not weathered by exposure to the sun, and they actually carried out another sampling attempt to pick up material that used to be underground and then was excavated by this. They also put several rovers on the surface of the asteroid, and this is just one sequence of images from one of those rovers as the sun, as the day goes by on this particular body. And the day here is about 6-hour rotation period. Sort of contemporaneous with the Hayabusa 2 mission is the NASA OSIRIS-REx mission. And this was launched just a couple years later and arrived at its asteroid Bennu. Here you can see again a size scale. Bennu is maybe a little bit bigger than Empire State Building, a bit bigger than the asteroid Itokawa. This is also a very primitive asteroid, carbonaceous material, and it's actually not back at Earth yet. We took the sample from the surface of this body in 2020, in the middle of the pandemic, and now the asteroid or the spacecraft is on its way back to the Earth, and it will actually re-enter over the Nevada test range this September 2023. So here, this is an image of the spacecraft with its sampling arm extended. Here you get to see one of the sampling, or the only sampling attempt that it took, where it came down and touched the surface of this rubble pile asteroid. And again, the geomechanics of this interaction were very interesting. Even though the surface of this asteroid, as you see here, looks like a sort of a surface of a gravel pit, when the sampling arm actually touched at a very low speed, it actually pushed into the interior of the body with almost no resistance, indicating that the material was in a very loosely aggregated state. Very unfamiliar from what we see on Earth. One of the motivations for studying this particular asteroid is also that it's one of the most potentially hazardous asteroids known. And in 150 years or so, it has a non-negligible probability of impacting with the Earth. So again, this scientific mission was a way to better understand what this body was made out of and how it could be mitigated if need be. Both the Hayabusa 2 and OSIRIS-REx missions, the spacecraft are still very well functioning. So they're actually each going off and carrying out additional scientific exploration of small asteroids, which is sort of a very interesting and unique aspect. I also want to just take a few minutes to talk about the DART mission, which I mentioned earlier was NASA's first planetary defense mission. And it was launched in 21, and last year, in September 26, it actually had an impact with the secondary of a binary asteroid system. And they actually were able to successfully measure how much momentum, how much impulse they were able to give to this natural body. And use that to come up with better understanding of the geophysics and the physics of this high energy impact, if you will. And there were other contributions, CubeSat that rode along from the Italian Space Agency, got to take pictures of the aftermath, and it also created a very large dust tail that was able to be imaged for months from the Hubble Space Telescope. So in next year, actually, the European Space Agency will launch the Hera mission, which will actually go to the same asteroid that the DART mission impacted and actually carry out a set of fundamental investigations of this particular body. It's also interesting because this will be the first mission to a binary asteroid, and will allow us to get more insight into how these peculiar objects actually form and evolve over time. So we can talk briefly about which asteroids we might be exploring next. The one that you may have heard of that's actually in orbit already, this is the spacecraft Lucy. This is a NASA mission run by the Southwest Research Institute. And this will be a mission that will actually explore and fly by the Trojan asteroids for the first time. And we believe that the Trojan asteroids are truly primordial bodies from the earliest planet-forming epoch of the solar system. So this will provide unique insight into those, although the mission time frame goes quite long. The first flyby is until 25, and the mission isn't done until 2033. Another mission that will be launching later this year is the Psyche mission, which will explore an asteroid that's believed to be the remnant core, iron core, of an early protoplanet. And this is, again, a very interesting motivation. And finally, I just want to point out that there are many other nations that are starting to become interested in exploring these asteroids. In particular, at the University of Colorado, we're working very closely with the United Arab Emirates and are developing a mission that will actually visit 7 different asteroids in the main belt. and culminate by orbiting the final object, the asteroid named Justitia, and going into orbit around that body, deploying landers to the surface, and carrying out fundamental scientific investigations. And here we're actually surveying members of the asteroid families that have not been visited before, again, widening our understanding of these bodies. Perhaps the ultimate motivation can be taken from some of the asteroids that we know about already. There's an interesting asteroid out there called 1950 DA, and it has a quite high probability of impact, but not until the year 2880. So it's quite a long time away, but it's a good thing to have in our vision, if you will. Its size is about 1 kilometer, and if it did hit the Earth, it would be large enough to create a huge impact. It could very, very well have dire consequences for humanity at that point. It's a very interesting body in that it spins so fast that it cannot be held together by gravity, meaning that, but we also know that it's a, if you will, a rubble pile body. So this is an example of a body that could be held together by very weak cohesive forces such as van der Waals forces, which is one of the leading ways of explaining why it spins so fast yet doesn't fall apart. But that's also interesting because if we try to hit this body, it spins so fast it may actually break up into several pieces, could absorb some of that momentum. Some of those lobes may actually remain on an impact trajectory, and it gives us a lot of interesting situations to deal with. So there are ideas and techniques that are out there to deal with it. One interesting one is called the gravity tractor, where we can actually use the attraction of gravity between, say, an artificial spacecraft and an asteroid, and use that attraction to slowly pull it out of the way. You have to be very careful, but you can, if you thrust, and if none of your propellant falls back on that asteroid, you can very, very slowly yank it out of the way, sort of like a very weak tractor beam. And there are variations of this that actually can increase the amount of push that you can give to the body by several factors. So with that, I appreciate the opportunity to talk a bit about asteroid and asteroid missions and asteroid explorations, and I'll be looking forward to some questions once we're done. Thank you.
Ladies and gentlemen, it is my great honor to come to this distinguished symposium with the distinguished speakers. So my topic is satellite proximity navigation for space debris removal mission. It consists of two parts. The first part, I'll be sharing with you what the space debris is, why it's so challenging, what is so important in the future space exploration. And second part, I'll share with you our recent progress in technology, navigation technology, using vision navigation in our lab. And the second also of this talk will be is Han-Hae-Yoon, who was my master student. She was not able to come, unfortunately, so I put her name because the technical part is her master thesis subject. Okay, this chart shows you since 1960s, ever since Sputnik launch, 1957, this annual increase in satellite launch. As you can see, year 2020, we have very sharp increase in satellite launch into space, in particular between 100 and 1,000 kilogram small satellite. And this increase also goes with the types of orbit, LEO. We have very sharp increase in LEO because of the recent mega constellation by SpaceX and other mega constellation project, we have a huge increase in LEO and also GEO. So as you can see, the number of satellites has been dramatically increasing in recent years. And the satellite missions are very critical and very important for our life and for the future technology development. And behind this, the background, we have the issue of space debris. Space debris is defined as inactive space object, which is not functioning somehow. And this space debris made of both natural type and man-made type. So as this along this material published by ESA, at the time we have 2,700 working satellites compared to 26,000 debris, almost 10 times more debris, 26 times more debris than the 2,700 working satellite. And this 26,000 debris that we can track by using ground station or ground equipment. But other debris, more than 100 million debris, even we are not able to track. We are not able to look at those more than 100 million debris because the size is less than 10 centimeters. Now we can track down debris greater than 10 centimeters in size. So this debris has been a big issue for future space development, big challenges. And there are some numbers, interesting numbers. There are approximately about debris, 20,000 pieces of the debris larger than softball. And they are flying very high speed, 17,500 miles or 28,100 kilometer per hour. It's very large speed. And there are more than 100 million pieces of debris greater than 1 millimeter and larger in size. It's a huge number. Even a very tiny paint black can damage spacecraft because this is large kinetic energy and large uncertainty because we are not be able to track those small debris. So a millimeter size orbital object can be a big damage to real spacecraft. And this chart shows you the increase in number of debris over the years, early 1960s to 2020. And as you can see, over last few years, almost 1 decade, the debris population density, very sharp increase. You can see here, in particular, year around 2006 and 2008. So at that time, what happened was that there was the accident, collision between Iridium and Cosmos, which is Russian inactive satellite. It was accident, and due to the accident, there was huge increase in debris population, about 3,000 debris generated through that by that accidental collision. And also China, 2007, they tested anti-satellite missile, and then that created some issue in international society. That test resulted in about 2,000 space debris and 15,000 fragmentation also. So this increase in sharp increase in population and also this density, heavy density around low Earth orbit, 800 kilometers, that orbit is very, very crowded with recent LEO satellite constellation. That has been a big issue in space society. So Sentinel-1 satellite also has been hit by space damage by accident. And that's one case of the collision due to gravity, the space debris. And there is a Kessler syndrome. What is the Kessler syndrome? Kessler syndrome, in 1978, he was a NASA scientist. He predicted that any space debris collision can increase additional collision in a cascaded form. So it can make things worse, creating further collision. That is Kessler syndrome. It's a very scary thing in the sense that the debris will be increasing dramatically. So 1 kilogram of object that can nearly 1 kilogram of object can damage 1,000 kilogram of satellite at large extent. So if you look at the debris size from 1 millimeter, 3 meter, and then 10 centimeter, you can see the right side that is equivalent to energy by collision through kinetic energy. So 5 centimeter collision with debris is equivalent to hit by the school bus, and 10 centimeter debris collision is equivalent to the energy produced by large bomb. And mostly these 5 and 10 centimeter size debris, they are trackable from ground facility, and those debris less than 1 centimeter, we are not able to track from ground. And let's take a look at lifetime decay. What is lifetime decay? Lifetime decay is the time it takes the debris to naturally decay its altitude and finally come back to Earth orbit and re-enter the Earth orbit and burn away. So those debris at geostationary orbit that takes few thousand years. It's really a long time until they naturally come back to re-entry phase. And debris at altitude of 1,000 kilometers, it takes a few decades until re-entry, and 800 kilometers, few years, and 500 kilometers, months. It takes very long time until they come back to us and they go to a re-entry phase, either by controlled re-entry, or it's very fortunate we can control them, but we cannot control all of them. So we do have uncontrolled re-entry also. So this chart, right-hand side, shows you the years it takes from a certain altitude, that how long it takes without any device or with the device. So if we have this device for deorbiting device, we can make this re-entry time shorter. And if we do not have that such device, this lifetime decay, it takes as long as more than 200 years. So this debris population increase and lifetime decay, it is, and also the dramatic recent increase in debris population. Those are the key issues why we should be concerned about this very challenging issue for human society. And the left chart shows you if you do some kind of debris removal mitigation, and if you can control the debris population by 2,200 years, we can do something. Okay, control this our space. But right-hand side, if we do not control the debris population increase, this is right-hand side figure, which looks very ugly, and then very dramatic exponential increase in risk and population, and that is creating another huge challenge, not only for space society, but also our other humankind in general. And how do you control, how do you, so far, how the global society can handle this issue? There is, unfortunately, there is the ground radar and facility that we can track the debris greater than 10 centimeter size. This space surveillance network, they were able to track the debris greater than 10 centimeter size from early 1960s, and then they were able to make a catalog and maintain the catalog. So they can track and they can predict all the trajectories of as many as 20,000 debris in catalog, and then they can predict any possibility of collision, and then they can give early warning that there will be possibility of collision, so that you should do some maneuver, orbital maneuver, that avoid that debris. So this is the way so far how people handle this issue, and give early warning by maintaining a catalog for debris, by taking ground facility such as radar and camera. Now with this warning and maintaining catalog, you can say it is a passive approach for controlling debris. Nowadays, there has been some recent effort how we can remove debris in an active manner, so that it has been a big interest for many new startups in global society. We have more than 100 startup companies working on active space debris removal. And among them, we have top 5 startups working on this active debris removal mission. So for example, we have Clear Space and Remove Debris, Start Rocket, and Astroscale. They're all working on active debris removal technology by sending chaser spacecraft, and approach the target and capture the target and execute the re-entry. And also remove debris mission that is very interesting, executed 2018, that the mission, they tested the net by capturing the debris by using net and also the harpoon and drag sail. So they recently tested some active debris removal technology on orbit, and they got some result, and which looks promising, but which are also challenging also, as I mentioned later. And how can we execute this active debris removal mission? So we have a target that is debris, and we have a chaser spacecraft. So the chaser spacecraft gradually approach the target, and finally they reduce their relative speed to 0, and finally they can make a docking and rendezvous on orbit. So we call it the far range rendezvous and close range and final range approach. So very close to distance, we call it the proximity approximation. For proximity operation, we have a chaser satellite and the target that can be space debris. So they're using a robotic arm and to capture the target. So in this mission, the critical technology is called the guidance, navigation, and control technology, GNC technology. So in this technology, our group is working on navigation technology, which is getting information, relative information between chaser satellite and the target satellite. That is navigation technology. And the guidance technology is guiding the chaser spacecraft to approach the target gradually. And the control is maintaining the attitude of a chaser satellite so that you can approach the target for the final proximity rendezvous and docking mission. So this is an animation by Clear Space. You can see that it approach and capture the target. Okay, in this operation, we call it the operative target. This target, they are not providing any information for their navigation information. So this unoperative target has been a big challenge in proximity operation because the target, they don't have any intention to provide their own information. So how can we get relative navigation information is very important issue in proximity operation. So we call it the relative pose that include relative position information and relative attitude information. And as you can see, the active, there has been some cooperative mission that they have some marker artificially designed, and target satellite recognize the marker, flashing marker, and then get some navigation information. Whereas non-cooperative satellite, they don't have any thing like this marker. So this our one chaser satellite, they should use a vision-based relative navigation by using monocular vision camera sensor technology. So how can we approach the target which is not cooperative, which is not providing any information for its own navigation information. How can we use vision camera so that we can get precise navigation information? That is a very challenging issue in the success of proximity operation. So we have this relative a little bit of mathematics here, which I do not explain the detail. We have this chaser satellite. We have target here, so they are flying each other very close proximity, and then the dynamics between chaser and the target can be described by relative translational motion and rotational motion. So with this dynamics, the spacecraft, how they interact together, how we approach the target, that is the goal of proximity operation. And then the navigation, we have this step-by-step procedure, so-called pose initialization and pose tracking. We are using visual camera to get the image, 3D image of the target and initialize the pose. And once the pose initialization is accomplished, then we go to pose tracking mode and constantly get the relative navigation information from the target. So how do you get the relative information for pose initialization? Actually, the target is a three-dimensional thing. So if you look at the satellite, the target, so it is three-dimensional world, and the camera is a two-dimensional, it's an image, a plane. So there is rotation and translation between three-dimensional world and two-dimensional image plane information. It looks a little bit complicated, but the principle it is very simple to understand. This is given, 3D is given. If we take it to the image, there is the target is rotating and target is translating with respect to the chaser, so that we can get those navigation information. That's the idea, whole idea of vision-based navigation for precise proximity operation. So if you look at this satellite here, this is a generic the target shape. So how do you discriminate this the shape so that we can discriminate the picture point of a target into from the image plane, and how do you get navigation information? That is the main idea. So we propose an idea that we use so-called the convex, the defect at this point. There is this continuity in the shape, so that computer vision is smart enough to recognize the discontinuity in the shape and use that specific picture point to estimate information and get the relative project data by solving the previous mathematical equation. There are many approaches already solving the 3D and 2D equation in vision processing already. We take advantage of that idea and we apply into this proximity operation. Okay. This chart explains the step-by-step procedure for that idea. The first one is image processing, and second one is we have intermediate pose estimation step first, and then precise pose estimation next step, and finally we have pose selection and initial pose verification. That is step-by-step by selecting candidate, the picture point, and then to image processing, and finally able to get precise pose between target and chaser satellite. So this is the algorithm that we are proposing. We call it the convexity defect-based algorithm, CDA algorithm, which is compared with the conventional Landsec algorithm, which is very well known in computer vision. And we have also simplified CDA algorithm that is a more simplified version of our algorithm. So we are comparing 3 approaches, and we are proposing our new idea is CDA and the simple CDA algorithm for comparison with the conventional Landsec algorithm. So this is simulation result. So this is the picture that's showing how accurately we can estimate the navigation information between target and chaser. The blue color represents we have a very highly accurate information, and the dark brown means we have a the bad information. As you can see, around all the target, the azimuth angle, 360 degrees, we tested it, and we tested the elevation angle 180 degrees. They are fairly doing very well in estimating relative navigation. And this blue color is kind of dominating over all 3 different algorithms. But our CDA algorithm here, we are able to save 50 times computational time compared to Landsec algorithm. So this is quite significant because we can implement our algorithm in real mission by having this such a improving computational efficiency compared to conventional Landsec algorithm. So this is a relative altitude error, very similar to position error for 3 different algorithms. Once we initialize this target state, then we are ready to continuously propagate the navigation information, so-called using a filtering algorithm. And this algorithm needs a little bit mathematics, but the basic principle is we are using the camera and get initial information and continuously propagate by using the previous initial condition so that navigation information successively updated by this border tracking approach. So this is the mathematics, and the details. We use the previous approach, and we just apply to our problem here. And the tracking, we use 2 approaches. One is a loosely coupled approach, where you are using this information directly. We have a tightly coupled approach also. 2 different approaches. We compare how they are showing different performance for this given problem. And this is simulation result. As you can see here, we have the target in the middle, and the chaser spacecraft is doing relative orbital motion. And we take the image and successively update navigation information while it is flying around the target. So this algorithm is working, and we have the simulation result here. So as you can see, our proposed tracking algorithm works very well. In particular, this tightly coupled approach is outperforming loosely coupled approaching. And this tightly and loosely coupled approach is well known in navigation society, and we simply reassure here that it is true, it is working well for our given problem set. And here we have a little bit a jump here signal because the solar array here, the target, the debris solar array is blocking the body, so we are losing observability instantaneously. That's why we have a huge error, the jump in error here for measurement error. So this is another, my last slide for my talk today. And the similar performance, and our tracking filter is working very well, and all relative XYZ translation information and attitude information, roll PTU, they are well updated over time and continuously with the reasonably small error, so that we can implement this idea into a real proximity mission. Okay, that's all I have today. Thank you very much for your attention. Thank you.
Okay, well, we covered all the space. From the Earth to the solar system to the entire universe. And also we covered from very, very massive black holes and neutron stars to very, very tiny objects. So I think we covered many orders of magnitude in scale and mass. So let me ask some questions to our individual speakers, and then I'll have some common questions to all of them. After that, I will open the floor for questions. Okay, first of all, Barish. LIGO's first detection of gravitational waves opened a huge door in science to unravel the secrets of the cosmos and the universe. And I think that it will go down in history as one of humanity's greatest scientific achievements. So congratulations. My question is that about the Lisa, that you ended your talk with. I'm curious to know the how LIGO impacted the science of LISA or technology of LISA, and also finally the funding agency's decisions on LISA.
I think the history goes back to almost the same time. LISA has a history that goes back to the early days of a funded interferometer project on the Earth. There was R&D work earlier, but basically they worked in parallel. At a place like my home institution, Caltech, the JPL was quite involved in the early work, and so there was a lot of interchange, some overlap in people, people that worked in LIGO going to LISA and so forth. Everything changed in the decade between 2010 and 2020. In 2010, there was the traditional priority setting in astronomy, the decadal survey, of which the highest priority for the next decade was the wonderful satellite that's up now, the James Webb satellite. And the second priority was LISA. And by that point, the technology was not proven, but it was meant to be a 50-50 collaboration between the US NASA and ESA in Europe. But as we entered the next decade, the costs for the James Webb Telescope escalated, and it basically removed from that decade the next two projects, an X-ray mission and LISA. That didn't stop LISA, because the European Space Agency basically then redefined it as one of their so-called corner mission, which is one of their big efforts. So its home has continued. But it's a European Space Agency mission. Now that the James Webb is up and we've spent all the money that we needed to on it, NASA has agreed to, I would call it a minor participation, but an important one scientifically of NASA in the mission. The timing has remained pretty constant. It's basically been in the early 2030s is when it's gone. There was scheduled along the way a test mission, which has happened and was, as I mentioned in my talk, very successful. So it's now in the basically early final engineering and production stage, but primarily as a European mission.
Thank you.
In terms of the overlap of people, there's quite a lot. The community has overall for gravitational waves an organization that we've created that looks at all the science and technology, and we meet together. And there's reasonable, so there's joint scientific meetings, there's planning, there's a lot of communication, and there's some number of people who are involved in both.
Mm-hmm. Thank you very much. Dr. Shiris, with your expertise in asteroid exploration, how do you envision the future of asteroid missions at the intersection of scientific exploration and commercial interest? Perhaps also another question, related question, is how might the collaboration between scientific research and commercial endeavors shape the trajectory of asteroid mining and resource utilization in the coming years?
Thanks. That's a very interesting question. And as I mentioned, the idea of resource exploitation of asteroids has been out there for as long as we've known about asteroids, I believe. But the ability of our spacecraft to actually interact with these asteroids and potentially extract material that could be used has grown tremendously over the last decade or two, especially with the Hayabusa 2 and the OSIRIS-REx mission. That being said, the pathway to making this a commercially viable enterprise still seems relatively distant, although there are entrepreneurs and visionaries who believe that they see a pathway to making this happen. And they are putting, in some cases, their own money behind their ideas. And it will be very exciting to see how they, what sort of success they may or may not have. One of the interesting aspects of it is to actually interact with an asteroid, to actually do some excavation there and the like, really requires you to understand the geophysics of these natural bodies at a level that we don't understand now. So if there are these successful missions to go and extract resources, they will have to have a fundamental understanding of how matter actually acts in this very low gravity environment that I was mentioning. And I think an analogy can be drawn with what you could argue is one of the original sciences, which is civil engineering, and our ability to understand earth and earthworks and dams and the like, and then our ability to use that knowledge to actually build infrastructure, transportation, mining, and the like. And you can envision similarly a civil engineering science to understand how to interact with and reshape these natural bodies and how that could feed back into an ability to take the material and produce some useful quantities out of it.
Thank you. Okay, let me ask one question to Dr. Bang. What do you see as the essential technological advancements needed to enhance the feasibility and effectiveness of space debris removal missions? Specifically, how will artificial intelligence play a significant role in addressing the challenges and complexities of such mission?
Thank you very much for your question. As I explained on over the recent success remove debris mission executed by ESA, European Space Agency. Actually, they intended many tests on orbit. Somehow they're having a lot of difficulties also because of the something they didn't expect in technically. For example, if you take a target by using camera, you have a very huge background sunlight that is bothering the capturing the image. And also when you take the image of the target, behind on the target we have a huge the Earth. So Earth image and target image, they overlapping together. So it is difficult to discriminate your target image out of the Earth background. There is a disturbance source. So in that sense, we need, in the long-term objective, we need artificial intelligence technology so that you can chase a satellite more reliably with high accuracy, being able to track, recognize the debris or target under all these disturbing sources, also background and the sunlight source. And that is the issue that right now the most people find out challenging in real active debris removal mission. So I would like to say the autonomy and the AI technology is a key element in future success of a space debris mission.
Thank you. All three areas, of course, your main goals are not the same, but I'm curious to know whether there's common interests in all three areas you can think of, or are there any interactions and collaborations going on in three communities? Anyone to take that?
In terms of the space debris problem and asteroid exploration and study, I think there are some key overlaps that occur. And in fact, ESA defines space debris as including the natural bodies that we've launched in Earth orbit and also the natural bodies that might strike the Earth. So they have a more expansive view of the topic. And I think this is because a lot of the fundamental technologies for understanding space debris and from arriving at and understanding a natural asteroidal body have a lot of commonalities between them. So yeah, there's an acknowledged overlap, if you will.
Yeah, I agree with Dan's comment. And if you think about your JASA spacecraft approaching small body and the debris removal mission, JASA spacecraft approaching the target debris. So there is a technology, as I mentioned, GNC guidance, navigation, and technology. So how precisely, how accurately you can approach the target, that is a key technology. So in that sense, we can share those technical elements together for asteroid exploration and space debris removal mission also.
Dr. Barish, do you have anything to add?
Yeah, I don't think, I mean, ours is a little abstract at this moment, and so I don't have any immediate synergisms that I can know of, except that I can imagine that the kind of manipulations that are needed for the asteroids are the kind of thing that's needed and will be needed as you develop the science and ability to have a very sensitive laboratory on these satellites themselves. But at this point, I think this is pretty primitive in comparison with that.
Okay, so now let me move to another question to all of you. Projecting into the future, let's say 50 years from now, how do you envision the state of your respective fields of study? What significant achievements do you anticipate in your fields? And what would be necessary to realize these ambitious goals?
I think since we're just starting, everything's a dream in space. We've done a little bit on the ground, but in space, it's all a dream. What I imagine is that we'll follow the path that has been done to do astronomy in space, the kind of missions. I don't think that they're fundamentally that much more difficult than the mission. The instrumentation is difficult, but that we develop on the Earth. But I think that the path will be very similar to the space experiments that are very much for doing cosmology or astronomy as we move, 50 years away from now.
Looking 50 years into the future in terms of asteroid exploration and science is I think, a huge topic. I think from a scientific perspective, I would expect that we would have sort of a mapping of material in the solar system and correlating that to where it formed in the protoplanetary disk and how it collapsed, so giving us further insight into that very early processes, what they call cosmochemistry of the planetary disk. I think we're now on a good path along that way with our sample return missions and some future ideas for sample return missions. In terms of interacting with the bodies, in terms of resource exploitation, at some level, I think there could be a correlation between us mapping material in the solar system, in the asteroid belt, and potentially investing in particular locations that seem to have a high value, although that still is very speculative. Even, I think for asteroid mining, even 50 years is maybe not far enough into the future, if you will, although of course things can happen very rapidly. And I think in terms of the impact hazard of asteroids, I do know that as time goes on, and actually in the next few decades, we'll have a much more detailed map of what asteroids are out there and what the true hazards are. And if we find no true hazards, then that gives us some breathing room in terms of worrying about this situation. But if we do find a hazard, some asteroid that might have a high probability of impact in the future, that could actually reshape a lot of global operations and global cooperation. So these are all possible, I think.
Well, about the 50 years of the vision for space debris issue, if you think about the number of satellites human being ever launched and operated since Sputnik launch in 1957, the total number was less than 3,000, 2,000 something, all including all over the world. And for last decade, there has been new mega constellation, so-called. So even if you look at the media, there has been the report Starlink will launch 40,000 satellites, and there is OneWeb and Amazon, and also Chinese government recently announcing 12,000 constellation in orbit. So altogether, there will be at least more than 60, and even more in the future. So it is a very scary thing that imagine how we can manage all the traffic, space traffic management, that even we can accommodate 100,000 satellites in the future. And that issue is a very practical issue. And not only for space society, but whole humankind also. So I imagine there will be a measure that we can, the robotic servicing satellite will collect all the debris, and also with so-called DOBIN module. So once your satellite lifetime expired, you have attached DOBIN module, so automatically re-enter the Earth's atmosphere, that so that we can completely eliminate a possibility of damage. So those technology will be mature in probably in the next 50 years. It's a very upcoming technology, I guess.
So in the context of, again, space exploration, all of you kind of covered about international collaboration in some level. I'm just thinking of future, how important international collaboration, among countries, but also among the different agencies, and if you have any thought on that.
Well, it's for the kind of thing that I'm talking about, I think it's essential from a resource level. I mean, I mentioned the fact that NASA had to drop out of that. That indicates the scale and cost and technical challenges that future astronomical and cosmological missions have. And so not duplicating, working together is going to be absolutely essential. And to a good extent, the groundwork is laid, but it's going to be even more important than before not to duplicate and to work together. Also, some of the technical challenges, I think the expertise is distributed around the world, and so having collaboration, I think, is going to be crucial for space exploration involving gravitational waves or astronomy, both.
Comments?
Yes, I also agree that international cooperation has played a fundamental role in a lot of the asteroid missions, and I think will continue to play a fundamental role. Just as a case in point, between the Hayabusa 2 and the OSIRIS-REx mission, both sample return missions to asteroids, there was a deep level of cooperation between the Japanese Space Agency and NASA, where they're sharing samples back and forth with each other. There are also many European researchers that are involved with these missions that can also access the samples, just as an example, from a scientific perspective. And then from the planetary defense perspective, it is of utmost importance to have a full international collaboration that goes on when people address possible risks to the Earth. And in fact, there are mechanisms that are set up all the way up into the United Nations for sharing of information, and there are frequent meetings that occur where people understand who the key people are in different countries in terms of the technology for mitigating these risks. So I think that forms an essential ground floor for progress.
You also agree with Dr. Bang?
Yeah, and I think space debris issue is one of the most elementary international cooperation and collaboration. United Nations already formed so-called IADC, Inter-Agency Debris Committee, something like that, as international collaboration framework for mitigating, reducing space debris. So they are providing some guideline when you launch a satellite, when you deploy a satellite, how to minimize the possibility of producing any debris. So all the government are recommended to follow that guideline. And also, if you think about space debris problem, it is not your own problem. It is everybody's problem working on space development. So there is highest priority collaboration. I think it should happen in space debris removal issue, I think. So that is something we have a more urgent issue, considering all the recent dramatic increase in satellite launch and delivery. So.
Right. So you all agree that international collaboration coordination is very critical. Perhaps I can ask you, what might be the biggest challenges for international collaboration and coordination?
Politics, as usual. I think the timescales, at least when you talk about science missions, the ones I talk about, the timescales are long enough so that politics changes. Of course, scientists and science has no borders, but countries do. And so I think politics is the biggest challenge, actually.
Yeah, I have to second that. Where there's many rivalries that exist across the globe, and that shapes how technology is or is not shared. It sometimes shapes, who scientists, especially who engineers, can talk to and can't talk to, and that does place a damper on things. However, how to remove the politics is difficult. If everyone agrees, with us, then okay, that's great. But politics, by its nature, doesn't have that as a solution, really. So it's a fundamental challenge.
What can we do? Can we do anything? How can you improve or stay away from politics?
Yeah, you don't have. I'll have a comment on debris and what is the challenge. And while you just think about it. Or?
Yeah. I mean, that's a fundamentally hard question. That's there are some questions that are called NP hard, because you can't solve them with a finite series of operations. And although I think science does provide a mechanism for collaboration that can be focused on something that's apolitical or non-political. And I think safety as well.
Right, safety could be also common
yes.
for everybody. So.
As far as responsibility issue is concerned, I think space debris is one good example. There has been a very wild debate on United Nations who is most responsible for space debris, which country. The country which is launching most satellite. So that issue has been there for a while, and they didn't come to the conclusion yet. And some other countries, new countries, they are now starting the space development. So it is difficult to say who is responsible and who take this who should pay for some money for handling that issue, things like that. That is the most challenging debris issue for as far as initiating when and how we'll start this space debris issue by putting some budget and who takes more leadership and collaboration. That is very challenging issue in space debris issue.
Okay, Barry, you have anything to add?
Yeah, I have a couple of short questions. It seems to me that I was impressed by the number of startups that you
That's right.
called. These guys aren't stupid. And so I think that indicates that a lot of people believe that a lot of money is going to be spent to remove the debris somehow. I mean, I find it a very good indicator, the fact that a lot of these companies obviously aren't going to succeed, but the fact that all them these startups have happened, to me is a strong indicator that there must be a good chance that the resources are going to come and follow it.
Yeah, I do agree with that. I'm very positive on your view that number of startups more than 100, and there'll be more in the future. And some people were asking me about that issue. Can they make any money by clearing debris? That was the question many people asking me. But I think they'll make money, and there are many reasons why they will make money in the future by having that advanced technology, because the technology is a dual technology. You can apply the technology into space, robot technology, by constructing huge solar plant, power plant on orbit, and you can also send robotic mission for on-orbit servicing, fixing the satellite which is not functioning, and also exchanging battery and refueling, things like that. There are many other applications by using that technology. So I'm completely agree with your comment views. Yeah.
And I have a second question for you.
Sure, go ahead.
So, you put it off in the distant future, but people talk about data mining, not data mining, mining on these asteroids. What is the geology or the belief in what it might be enriched with that would actually make that a feasible goal or a plausible goal compared to mining on the Earth for whatever it is, that gold or uranium or whatever? I don't know what the key things are that you might find.
Yeah, that's a great question. In the popular press, there was a lot of noise about the Psyche mission to asteroid Psyche, that there was enough platinum in this asteroid to, it's like, how many trillions of dollars. Of course, it's completely useless sitting over there, right? And the value in resource extraction is that you can utilize materials that you don't then have to launch from the Earth, because that's a very expensive proposition. And I've heard talks about various ideas of what people want to develop. And probably the most compelling ones I've heard is either extracting water out of some of these primitive asteroids, because they do actually contain a fair amount of water, because water has many purposes, and you can use it for propulsion and shielding and the like. Or also there's some ideas about utilizing just the silicate rocks that exist in abundance that you can then use and maybe transform through some process into large-scale space structures for like solar power and things like this. So those are the best ideas I've heard.
But the key is to use the material out there, not to bring it back.
Exactly.
And compete with mines here.
No. Yeah, you can't do that. And in fact, you can imagine huge disasters if you send too big of an asteroid back to Earth.
All right. Well, thank you very much for those conversations. Let's take a couple of questions from the audience.
So your exploration by gravitational wave is mostly on binary black holes so far.
So far.
Yeah. But you know about this James Webb Space Telescope is looking far beyond. So do you see any possible, what's the role or the, because the way we look for the space, it's limited by just looking at the black holes, especially binary black holes. So what would be the role of this gravitation wave detection compared to James Webb Space Telescope?
Well, we're not limited to just binary black holes or binary systems. That's just because it's the loudest signal, and we're the poorest in terms of developing the ability to detect signals. So let me give you some examples of other signals. First, supernova, the collapse of a star. Those are common, but the problem now is that in our own galaxy, although if we calculate the life and death of stars, we expect to see a supernova once every 20 years in our own galaxy, but we haven't seen one since Galileo. And so something's wrong with that calculation, but that isn't very much, so we have to see further. And so if you ask how many supernovae there are where there's one a year, you have to go out to the Virgo cluster. And we're not good enough yet to do that. But studying a supernova, which is a gravitational collapse with gravitational waves, is probably the best way to have a real understanding of what the collapse is, why it makes whatever final products it does, and so forth. A second example, so I'll give you three altogether that are very different. It's not everything, but the second example of gravitational waves that we anticipate, I would say we'll see a supernova sometime, but you can't predict when. The second is very attractive, and that is to see a spinning neutron star in our own galaxy. And what the problem there is a technical problem. There's plenty of neutron stars or pulsars in our own galaxy, but our ability to look for them is limited by looking for ones that already are known. And the reason is you have to track this thing around. And so we take and look for pulsars that are found by astronomers in radio telescopes. They give radio signals. But by definition, in order to give this very constant radio signal, they're very old pulsars. So the star has collapsed, and then sometime way later, they've gotten rid of all the asymmetries they have, and they're very constant, and the radio astronomers see them as a very constant signal. But the gravitational wave signal comes from having a non-totally spherical system, like when two black holes come together. If we can detect them, which I think we'll be able to eventually, we're limited by computer power more than instrumental in this case, to be able to look for ourselves rather than at targeted ones that astronomers have seen. If we can see them, then we have the nice feature, which is different than what we've detected now. The event is not episodic. We can then keep looking at that pulsar or whatever it is, that spinning neutron star. As we develop future instruments, it's known just like we know certain stars or galaxies that we're pursuing astronomy. So then we're really doing gravitational wave astronomy. The last, which I'll mention, is something that we can do that we cannot be done with electromagnetic for sure, and it's important, and that is to see the signals that come from the early universe. So the way to really look at the early universe is with something that wasn't absorbed, and that's gravitational waves. So we look now for stochastic background that would come from the early universe, but we're not very optimal for it. We're just barely good enough to see these black hole mergers, and we're at very high frequencies. But as the science develops and the sensitivity gets better and people develop the detectors that work at lower frequencies, I mentioned some, then we start to be able to hopefully see signals. We can't predict them because we don't understand the early universe very well. There's features, what are called inflation, that's just phenomenological, but we don't know what they are. We can take models now and certainly estimate that they could be detectable in future detectors, not in LIGO, but in future detectors. So I've given you examples of something that can be a continuous source, something that's not binary black holes, but the collapse of a star, and understanding the early universe. So I think the scope of things is just limited by our how slow it takes to do it technically. It's taken 400 years, I'll remind you, for us to develop astronomy to where it is now. We started with Galileo in 1600s, and so give us a few more years and we'll do some stuff with gravitational waves.
Great. With scientific breakthroughs and technology breakthroughs, we have unlimited opportunities to explore space. With that, we conclude today's Scientific Innovation Series, New Era of Space Exploration. Let me thank our speakers once more for the informative talks and discussions. And I would like to extend our heartfelt gratitude to all of you for making this event truly special. And thank you to our viewers on YouTube as well. Thank you very much.